Hello, IS31006. A very pleasant morning to all of you. And yes, today we are going to witness our presentation for Sensors Engineering. Welcome to Sensors Engineering, Position Sensor Reporting. To formally start our position sensor, let us have first our recap on what is a sensor. So ano nga ba yung sensor? So, sensors are a part of everyday life at home and work. There's probably not a day that goes by where aren't impacted in some way by a sensor. A sensor is a device that senses something. Today, we have sensors that can see, feel, hear, smell, and even taste. Without sensors, our home and work lives would be quite difficult. A sensor is a device that detects and responds to some type of input from the physical environment. The input can be light, heat, motion, moisture, pressure, or any number of environmental phenomena. The output is generally a signal that is converted to a human readable display at the sensor location or transmitted electronically over a network for reading or further processing. Sensor plays a pivotal role in the Internet of Things. They make it possible to create an ecosystem for collecting and processing data about a specific environment. So it can be monitored, managed, and controlled more easily and efficiently. So next is what is a position sensor? So position sensors are devices that can detect the movement of an object or determine its relative position measured from a established reference point. These types of sensors can be also used to detect the presence of an object or its absence. So the position sensor is a device that collects information on the precise position and movement of an object. The information can be obtained by a direct contact with the object or remotely using magnetic sensors. So it can also detect the thickness of the part, the level of a fluid, or the angle of the rotation of a device. The position sensor is essential for the correct operation of different machines, such as machine tools. Next is position sensors are used throughout many industries for many applications in motorsport, agriculture, industrial application, and etc. And are also used in devices which surrounds us, such as elevators and moving ramps. Position sensors are even used in the special effects of department of different firms.
Types of position sensor. Potentiometric position sensor, or also known as a resistive sensor, measure the resistance of a conductor track between a reference point and a cursor attached to a moving component or its support. The resistance of the sensor is used to compute the component's location. It translates the distance or displacement of item in a linear or rotating motion into electrical signal. Yun nga daw po. Ang potentiometric position sensor or kilala sa resistance sensor, ito yung nagme-measure ng distance or displacement ng isang bagay sa isang linear or rotating motion into electrical signal. Ang sensor na ito ay napaka-accurate at ang mura. Pero ito ay sila ay yung madalas masira mula sa vibration, mga alikabok, at sensitibo ito sa high temperature. Meron tayong maraming pwedeng paggamitan ng potentiometric position sensor kagaya na lang ng sa in robotic application, computer game joystick, in automotive industry like yung sa steering wheel at yung sa throttle position. Pwede rin ito sa aerospace application tulad ng paggamit sa flight control at fin actuation. Pwede rin ito sa medical application. Next one po ay yung capacitive position sensor. Capacitive position sensor is a non-contact measurement method as the system does not make contact with the part. There are no witness mark, part of distortion, or probe wear. Since there is no sensor cycle time, high volume measurement are achievable. Ito nga daw po, ang capacitive displacement sensor operate by measuring changes in electrical capacitance. Capacitance describe how two conductive objects with the space between them respond to a voltage difference applied to them. Ang capacitive sensor ay nakakapag-measure po siya ng mabilis. Tulad nga po ng sabi, ito ay non-contact device. Kaya may kakayahan ito magsukat ng matataas na resolution ng position o change of position of any conductive target. Tamang-tama po ito para sa mga aplikasyon ng pagsusukat ng high bandwidth at high volume sorting application. Nagagawa rin po nito sukatin yung kapal or density ng mga non-conductive na materials tulad ng kahoy, bakal, or thickness po ng mga salamin.
Ang linear variable inductive transformer naman ang siya nagko-convert ng linear displacement upang maging electrical signal. Ang mutual induction, ito ang pinakamabisa na gawin lalo na kapag ang flux of primary winding ay na-induce sa secondary winding upang makuha ang output ng transformer na kinakailangan na kunin ang difference ng secondary voltage at yung tinatawag na differential transformer. Ang eddy current ay circular current na na-induce ng isang conductor kapag ito ay pinanatili sa isang nagbabagong magnetic field. Ginagamit ang eddy current sensor bilang a proximity sensor upang makita ang presence or absence ng non-magnetic conductive material. Ito ay isang non-contact sensor. Ang Hall effect sensor ay solid-state device na nagsiswitch sa active state kapag ito ay pinakilala sa isang magnetic field. Ang output voltage ng Hall effect sensor ay nakasalalay sa magnetic field sa paligid nito. Kapag ang magnetic field sa buong semiconductor slab ay nagbabago, ang magnetic flux density ay nagbabago rin dahil sa kung saan ang output ng voltage ng Hall effect sensor ay nag-iiba.
Resistance-based position sensors or potentiometric position sensors. It uses a potentiometer which measures the distance moved by an object, linear or angular, and converts it into electrical signal. It has a wiper contact connected to a mechanical shaft that is free to move across the resistive track. So the movement caused the resistance between the wiper and slider to change. So we know that the resistance is equal to rho times L over A. So wherein rho is the resistivity, L is the length of the wire, and A is the area. So therefore, the resistance is directly proportional to the length. So whenever a body moves, the wiper moves across the resistance, giving an output voltage which will be proportional to the position of the wiper's resistive track, and hence the value of the resistance. So we can see in the figure both in linear and angular position. We can find the output voltage as under ideal condition. The ratio of V out by V in is equal to Li by Lt, wherein Li is the distance moved across the resistive track, and Lt is the total length of potentiometer. So we have here a three known quantities, V in, Li, and Lt. So we can easily find out the V out, which will be proportional to the distance moved. Capacitive position sensors. So these are non-contact sensors which detect change in capacitance to measure the position of an object. So here is the formula of the capacitance. So we know that capacitance between any two plates is given by C is equal to A epsilon 0 epsilon R over D, where A is the area, epsilon 0 is the permittivity of the dielectric between the plates, D is the distance between the plates, and epsilon R is the relative permittivity of the dielectric. So we can see capacitance, area, distance, and dielectric constant. So by changing each of these parameters, we can change the value of the capacitance. So we can measure the position in terms of changing capacitance. So there are two ways. First, we can alter the dielectric constant of capacitor. So as you can see in the figure, here we will connect the body whose position is to be measured to the electric material between the plates. So whenever the body moves, the dielectric will change and hence the capacitance. Thus capacitance becomes the function of the body's position. So the second way is we can alter the distance between the plates. So we can make one plate fixed and the other is movable. And the body whose position is to be measured is connected to a movable plate. So whenever the body moves, the spacing between the plates will change, hence the capacitance will change.
So now let's proceed to linear variable differential transformer, or the so-called LVDT. So we can see when an AC source is activated, alternating current starts flowing through the coil. It is due to which varying magnetic field is produced. Now, when this varying magnetic field interacts with the secondary coil, an EMF is induced into the secondary coils. Next is we see that initially the core is in such a position that equals EMF gets induced in both the coils, due to which the net EMF of the secondary coils becomes zero. This position of the core is known as the null position. Now, if we move the core towards the right, we see that the flux linking with the coil S2 becomes greater than the flux linking with the coil S1. As a result, the EMF, the EMF induced in the coil S2 becomes greater than the EMF induced in coil S1, and the net EMF shows a negative value. Next is similarly, if we move the core towards the left, we see that the flux linking with the coil S1 becomes greater than the flux linking with the coil S2, as EMF induced in coil S1 becomes greater than the EMF induced in coil S2, and the net of the EMF shows a positive value. Thus, the LVDT uses a magnitude and polarity of the net EMF induced to measure the displacement of its core from the null position. Next is the eddy current position sensor. So yung eddy current sensor operates based on the inductive eddy current principle. So it measures the distance based on the interaction of energy from an isolating circuit, which is required to generate eddy current in an electrically in conductive materials. When the sensing coil is supplied with an alternating current, it causes a magnetic field to form around the coil. If an electrically conductive material is placed in this field, eddy current field is induced according to the Faraday's induction law. When the object moves, it causes change in the impedance of the coil, which is proportional to the change in the distance between the sensor and the target. Moving on to the Hall effect based on magnetic position sensor. So yung Hall effect sensors are activated by a magnetic field, and in many applications, the device can be operated by a single permanent magnet attached to a moving shaft or device. So there are many different types of magnet movements such as heads-on, sideways, push-pull, or push-push, and etc. sensing movements, which every type of configuration is used to ensure maximum sensitivity of the magnetic lines of flux must always be perpendicular to the sensing area of the device and must be of the correct polarity. So yung build-up of charge carriers creates a potential difference between the two sides of the semiconductor material as electrons and holes migrate sidewards. The existence of the external magnetic field at right angles to the semiconductor material then affects the passage of electrons through it. And this impact is higher in flat, rectangular shaped material. The Hall effect is the result of the employing a magnetic field to generate a quantifiable voltage. Magnetic flux lines must be perpendicular at 90 degrees to the current flow of the correct polarity, often a south pole, to generate a potential difference across the device. The Hall effect reveals the type of magnetic pole as well as the amount of magnetic field. Also, it is to ensure linearity. High field strength magnets are required that produce a large change in the field for the required movement. There are several possible paths of motion for detecting a magnetic field, and below are the two common and below are the two more common sensing configuration using a single magnet. Ito ay yung tinatawag nating head-on detection and sideways detection.
Next is dumako tayo sa construction of types of position sensors. And number one is resistance-based or potentiometric position sensor. So, dito, konting background lang or kapag nagugulan kayo, i-discuss ko lang about yun sa potentiometers or potentiometric position sensor. It measures EMF or electromotive force and cell resistance. It compares cell EMF. Most applications use it as a variable resistor. So potentiometers are used in a large quantities to adjust electronic circuits for correct outputs. Their most obvious uses is on the radios and other audio equipment. For the main topic sa part nito is construction of these different types of position sensors nga. And number one is potentiometric position sensor. All you need to make a potentiometer is a long resistive wire L na makikita nyo sa slide of magnum or constantan. Pag sinabing constantan, it is a copper nickel alloy used in electrical work for its high resistance. And the battery with the known electromotive force or EMF nga, driver cell voltage describe this level of energy. Assuming this is a primary circuit na nasa PPT, yung nilagay ko dyan na nasa figure, and it connect the two ends of the resistive wire L to the battery terminals as shown below. To measure the EMF of a different cell, one end of its terminal is connected to the primary circuit and the other end is connected to the resistive wire at any point via a galvanometer. So, when it's a galvanometer, it is an instrument that can detect and measure small amounts of current in an electrical circuit. So let's pretend for a moment that this setup is supplementary circuit. This is how the potentiometer is set up.
Capacitive position sensor. Ito po ay device na nagdedetermine sa displacement ng dalawang parallel plates. Ang isa dito ay ang sensor at ang isa ay ang object or material na minemeasure ng sensor. The measurement technique of capacitive sensing is non-contact. There are no witness markings, part distortions, or probe wear since the system does not make contact with the part. High volume measurements are feasible since walang sensor cycling time. They are perfect for sorting applications with massive volumes of data as well as high bandwidth measurements. Ang capacitive sensor ay nagbibigay ng very high resolution matched only by the laser interferometer at ang common resolutions range from 0.1 nm to 50 nm. Operating ranges are generally less than 3 millimeters. So technically, Capacitive position sensor has two major parts. The first one is the active sensors. Sa active sensors, ang cable length restrictions ay hindi applicable sa active system. Ang active sensors ay nag-ooperate sa higher frequencies and output bandwidths. Appropriate din sila sa mga applications like spindle run-out analysis that may involve stray electrical noise on the target. Active systems have fewer configuration options and higher cost, among other disadvantages. The other one is the passive sensor. Passive sensor has some advantages in terms of stability, probe configuration, and price. Nag-o-offer din sila ng greater versatility. Pero due to their restrictions in cable length, driving frequency, and bandwidth, hindi sila suitable for many applications unlike sa active sensors.
So next is LVDT or linear variable differential transmitter. So it is consists of cylindrical former that is surrounded by one major coil in the hub of the former and two minor copper coils on the surfaces. The number of turns in each minor coils is identical, but they are wound in opposite direction, the clockwise and the counterclockwise. For this reason, the output voltages will be the variation in voltages among two minor coils. These two coils are denoted with S1 and S2. The S1 and S2 are switch designation in the recommended wiring schemes. When these switches are wired as indicated the S1, it is for freewheel stop operation. And for S2 naman, it is soft start operation. Steam iron core is located in the middle of the cylindrical former. The excitation voltage of alternating current is 5 to 12 volts and the operating frequency is given by 50 to 400 Hz.
Another type of position sensor is the eddy current sensors. Eddy current sensors are non-contact position sensors used to track a target's movement over time. High-resolution measurements are possible with eddy current sensors, which are also known as inductive sensors. Magnetic fields allow eddy current sensors to function. A sensing coil at the end of a probe receives an alternating current from the driver. The alternating current then generates an alternating magnetic field that induces eddy currents, smaller currents with the target material. The probe coil's field is then opposed by an opposing magnetic field produced by the eddy currents. The interaction of the magnetic field is dependent on the distance between the probe and the target. The changes in field interaction can then be used to calculate the distance between the probe and the target. And an output, it is generated that it is proportional to the change in distance. Why, why choose eddy current sensor? Is because they are high precision and are often selected for applications because they have tolerance in dirt. They still work even though there is something between the probe and the target. And lastly, they are less expensive than capacitive sensors and they are also unaffected by contaminants.
And for the last part, Hall effect-based magnetic position sensor. So it included a thin rectangular slice of P-type semiconductor material, such as gallium arsenide, indium antimonide, or indium arsenide that conducts a constant current. The charge carrier's electrons and holes are pushed to one side of the semiconductor slab when the device is put in a magnetic field due to the force of magnetic flux. It is acting on the semiconductor material. The charge carrier's motion is caused by the magnetic field force that they encounter as they traverse the semiconductor. As the electrons and holes accumulate on opposite sides of the semiconductor material, a potential difference is generated, and the existence of an external magnetic field perpendicular to the direction of electron motion in semiconductor material has a higher impact on a material with a flat rectangular shape. Next slide po, thank you. Both linear and digital outputs can be found in Hall effect sensors. The voltage at the linear analog, and it is proportional to the magnetic field that has passed through the Hall sensor. Hence, the voltage serves as the sensor's output signal. And next, makikita nyo po sa figure na nasa PPT, yung formula where V sub H is equal to R sub H times the quantity of I over T times B, where V sub H is the Hall voltage in volts, and R sub H is the Hall effect coefficient, and I is for the current flow through the sensor in amps, and T is for the thickness of the sensor in millimeter, and B is the magnetic flux density in Teslas. For linear or analog sensors, it generates a constant voltage that increases with a strong magnetic field and decreases with a weak magnetic field. In linear output Hall effect sensors, as the magnetic field intensity increases, the amplifier's output signal rises until it saturates due to power restriction. Any increases in magnetic field will not affect output but saturate it. And for digital output sensors naman, it uses a Schmitt trigger with built-in hysteresis when the Hall sensor's magnetic flux surpasses a preset value. The device output flips from off to on without contact bounce. So, okay guys, so when we say a Schmitt trigger, it is a logic input circuit that uses hysteresis to apply positive feedback to the non-inverting input of a comparator or differential amplifier. It's allow guys na yung output to retain its value until the input charges sufficiently to trigger a change. Built-in hysteresis eliminates output signals as the sensor moves in and out of the magnetic field. Digital output sensors are on or off. Yun lang po.
As stated a while ago about the definitions and introductions of position sensors, now I'm going to share some of the applications. First was the robotic applications. They are used in rotation of a robot's wheel to determine its distance traveled along the ground. Next was the computer game joysticks. Third was the automotive industry, where its angular position sensor can be used for throttle position, steering wheel position detection, and most systems that acquire an accurate angle reading for operation equipment. And it also have an aerospace applications where it includes fin actuation, flight controls, and valve position measurements. And last was for the medical applications, wherein linear and string potentiometer relied on the precisely measured position in robotic devices. And for the second application of position sensor, which is the capacitive position sensor, and its applications are first in the semiconductor industry. The silicon wafers need to be positioned for exposure. And next was the capacitive sensors are also used to pre-focus the electron microscopes used in testing and examining the wafers. The sensors are used to analyze and optimize the rotation of spindles in various machine tools, which mostly examples are surface grinders, lathes, milling machines, and others. and also in assembly of precision equipment such as disk drives. And last was in precision thickness measurement and assembly line testing.
Hello everyone, today I will be discussing about the applications of position sensors. The first one will be the Linear Variable Differential Transformer, or LVDT. LVDT is used to measure the physical quantities such as force, tension, pressure, weight, and etc. These quantities are first converted into displacement by the use of primary transducers, and then it is used to convert the displacement to the corresponding electrical voltage signal. It is mostly used in industries as well as a servo mechanism. It is also used in industrial automation, aircraft, turbine, satellite, and hydraulics. When it comes to LVDT sensors, there are plenty of applications to be aware of. For instance, where LVDT sensors have a wide array of potential applications, one of the most common sectors in which LVDTs are used is the space and the industrial realms. With that in mind, the first thing will be the defense satellites and launch systems. In terms of defense satellites, a benefit we get from using LVDTs is that they help position satellite panels towards the sun. This helps us get the energy from the sun onto the satellites to keep them floating in space. As far as launch systems are concerned, LVDTs allow for optimal performance while needing minimal maintenance. This is ideal when dealing with launch systems as they may frequently inaccessible and difficult to service. Next would be about valve pitch actuators. LVDTs play a major role in their overall functionality. For instance, the sensor serves as a tool for confirming that the valve actuator has moved in the proper position, ensuring it functioned properly. Another one to include is engine bleed air systems. When it comes to engine bleed air systems, they are used to help regulate the amount of air being bled into the system. This is how it creates energy and uses fuel to optimize the engine's performance. One important application of LVDT which aids mostly all types of transportation is about the fuel controls. As far as fuel controls are concerned, an LVDT helps to ensure the fuel is being optimally used at all times, thus making sure it's releasing the fuel at the optimum time of performance. It gives us the proper performance to fuel ratio. Lastly, a linear displacement transducer provides feedback in terms of the valve position to show that they're helping to control the actuator and that they're helping to monitor or manage the valve position. And this is with the help of LDVT in valve position feedback. And for the next sensor, as we call it, eddy current position sensor. Due to its resistance and stability to measure under extreme environment, eddy current sensors are used in a wide range of industrial applications. Some examples include measures vibrations of actuators in steel galvanizing plants, cylinder movements in an internal combustion engine, measure thickness of sheet metals in roller gaps, measure movement of hydraulic cylinders, and are used in airplanes to measure movement of door lock switches and landing gear flaps. Some other applications of ECPS are crack detection. Eddy current crack detection equipment can be divided into high-frequency instruments for finding surface breaking cracks in ferrous and non-ferrous materials and low-frequency instruments for finding subsurface cracks in non-ferrous materials. Tube and wire testing. Automated eddy current test systems have been developed for inspecting tube, bar, and wire at speeds up to 3 meters per second. Once the operator has calibrated the instrument using a tube or wire with known flaws, the test installation runs automatically, ejecting defective pieces from the production line or marketing them with the paint. Material sorting. Ferrous segregators and electronic sorting bridges are useful tools in sorting steels, which have been hardened. Conductivity meters can be used to sort aluminum and copper alloys, both for compositional variations and hardness variations. Because eddy current fields penetrate below the surface of the test material, the method provides a better sample of material properties than many other material sorting methods, and more importantly, it is very rapid. Coating thickness measurement. The high near surface resolution of eddy current testing makes it used for accurately measuring coatings, both metallic and paint, on metal substrates. Moving on to the next sensor, Hall effect-based magnetic position sensor. The applications of Hall effect sensors are as follows. When combined with threshold detection, they act as a switch. These are used in ultra-high reliability applications such as keyboards. It is also used to time the speed of wheels and shafts. Used to detect the position of the permanent magnet in brushless electric DC motors. Used as embedded in digital electronic devices along with linear transducers. Sensing the presence of the magnetic field in industrial applications. Used in smartphone to check whether the flip cover accessory is closed. For contactless measurement of DC current in current transformers, Hall effect sensor is used. It is also used as a sensor to detect the fuel levels in automobiles. Some of the examples for the application of Hall effect sensors are the current transformers, position sensing, accessories, keyboard switch, computers, proximity sensing, speed detection, braking systems, magnetometers, DC motors, disk drives, and others. That's all. Thank you.
So next is the selection sensor. So first we have potentiometers. These potentiometers are often the cheapest option for the position sensing but needs the physical contact with the moving target. Next is the LVDTS. Sila yung mga yung presyo nila ay highly but can tolerate dirty or harsh environments. They offer high accuracy, high precision as well as high sensitivity, and also they find application in industrial and aerospace applications. Ang next naman natin is yung optical sensors. So dito naman, they have very fast response as they are non-contact type and light in weight. However, proper alignment and protection from harshy and dust environment is necessary, and also they are relatively cost. Next is the Hall sensors. So sila yung cheap but are used in on or off type of application. It is effective only for application where detailed positions information is not required. And lastly, yung ating eddy current based position sensors are moderately priced but are not preferred in applications in applications requiring highly detailed positioning information or very large gaps exist between the sensor and the target. So, sila yung they can tolerate dirty environment and are good when mounted on a stationary mechanical structure.
What is the importance of position sensor and the difference of position sensor to, to other sensor? Position sensor, it is a sensor that used to detect object movements and convert into signals, which are suitable for transmission, control, or processing. Itong sensor na to ay ginagamit upang makita yung mga paggalaw-galaw ng bagay, tapos kino-convert po ito sa isang signal. So, these sensors are normally used for measuring the distance of a body from reference point. A position sensor is any device used for measuring the distance traveled by a body starting from its reference point. It's measure linear or angular position in reference to a fixed point or arbitrary reference. In general, the difference of position sensor and other sensor, it detects or sense the movement of object and also measure the distance between established point. Kumbaga po sa general, ang position sensor po is mine-measure niya yung mga distance, nagde-detect po siya ng mga movements, yung from point to point na measurement. Tsaka po, ang position sensor po, malaki po yung role niya sa daily lives, lalo na po sa mga machine natin, sa mga cars, sa mga workplace, lalo na po talaga sa mga kotse. Sobra po laking pakinabang ng position sensor kasi po, kung wala po nito ay possible po na madaming mga aksidente.
To sum up our report about position sensors offer position feedback as its name suggests, by assessing whether a target is present or absent, or by detecting its motion, speed, direction, or distance. They may carry out precise motion control, encoding, and counting functions. Position sensors turn a physical characteristic into an electrical output to show the target's position when they encounter a target object, person, substance, or disruption of a magnetic or electrical field. Furthermore, at this report, we've tackled the different types of position sensor, namely potentiometric position sensor, capacitive position sensor, linear variable differential transformer, eddy current position sensor, and lastly, the Hall effect based magnetic position sensor.